Hello everybody, it is July 2023 and today I would like to present you one other paper of our climate series papers. This one presents some contemporary climate data and I have dubbed this one the Pinatubo event. It is presented in the journal Natural Science, where it is open access, so you can get it there for free. If you want, you can also find this and other papers in my private website. It's stalinga.org. There are links there and everything is open access. So once again, buckle up and let's get started. First of all, as we know, there were a lot of United Nations climate conferences, and this is all based on the link between the carbon dioxide in the atmosphere and the temperature on this planet. Allegedly, we are suffering from global warming because of the extra carbon dioxide that we're emitting into the atmosphere. So everything here is based on this carbon dioxide in the atmosphere that you see here. That's the green signal. It comes from Mauna Loa, that is an island on Hawaii, and that is basically the data we're going to analyze today. Also note here that there were a lot of this conference of participants, I think it's called, the United Nations climate conferences, and as you can see, the first observation is that all these conferences had no effect whatsoever on the carbon dioxide kinetics. So they're basically, the first observation is that they're a waste of time and effort. And this actually then, let's start here with some kind of political statement, because as a scientist sometimes we get a little bit angry with these politicians which assuming the role of scientist. So now it is time for some counter-offensive that Mr. Angus made his first law, and that said that, and this perfectly applies to the United Nations and these COP conferences, all human organizations tend to be self-amplifying. There's an effect which hamstrings all corporations, even the most effective ones. It is the natural tendency of any organization to become ever more what it already is. This is called the self-amplifying tendency. The longer an organization has spent becoming more as it is already, the stronger is the force to pushing it in the same direction, like matter being sucked into a black hole. Eventually, it will lose the ability to change at all without recognizing how it happened. Well, look around you. What other human organizations are behaving like this? Will any human organization ever say, we are actually redundant and we close ourselves? Or will they reinvent whatever enemy it is that they are invented and continue on the path that they already went? So, to show you that these conferences had no effect whatsoever, there is no climate change caused by carbon dioxide, as I have very well shown in earlier in other videos. Find them in stalinga.org if you're interested. So they still keep on banging the same drum and going on and on and on. Today we're going to find another nail in the coffin of their model. We're namely going to analyze contemporary data, and we will show that also here their model fails and they should basically close shop. So we're going to look at this carbon dioxide in the atmosphere and analyze what is going on there. So you see here the sort of like exponential rising tendency, and on top of that some oscillations. What we did here, we fitted an exponential curve with the time constant, and we fitted a sinusoidal effect on top of that with a periodicity of 1 year. Okay, so this gray, I just offset it so that you can see the two, otherwise you cannot see them very carefully. But in the next plot I will put them together, but you will see that this gray curve is what has been simulated with an offset here, presented here as an offset, and the green one is the observed data. Well, you can see yourself that it looks very nice, exponential, but something seemed to have happened here, and as we will show, it's in 1991. So what is this thing? Just for your information, the fitting parameters of this one here is given in this table, and then I put them together and you see the residuals. that if I fit only up till this point, and you can clearly see that it fits very well until 1991, and then it will deviate from the fit, and it was supposed to continue to rise, but actually the kinetics have slowed down. Okay, and now comes the important thing. We also know our carbon emissions. So let's put this year-on-year change of this curve. So we're not looking at the periodicity here, but we take the year-on-year change from this data. So we take, for instance, May 2001 minus May 2000, and that plot as a data point. And then we get this curve here. So in red are our carbon dioxide emissions from fossil fuel burning. So these are very well known, and actually they are not very noisy. As you can see yourself, our economy is steadily growing, steadily increasing the amount of wealth in the world, and they're not so much, they don't have so many variations on it. But when you look at the year-on-year carbon dioxide measured in the atmosphere, measured at Mauna Loa, you see it's very erratic. It is very noisy. So the first observation, how can carbon dioxide measured in the atmosphere fluctuate if carbon dioxide is caused by humans? These are not small fluctuations, they're very big. Why does this blue one not follow the red one? And actually, it may be an even worse effect that you see here. I plotted them here. Red is the emissions, and blue is the year-on-year change of carbon dioxide in the atmosphere. But note also that I had to rescale them. The blue scale goes here to 25, while the red scale goes to 50 gigaton per year. So a factor 2 is missing here. How can it be? Immediately 50% of all our emissions are missing. And they said that the atmosphere is very stable, and it takes very long time, centuries, for carbon dioxide to possibly be removed from the atmosphere. Well, not so. We inject 50, and what remains is 25. Half is missing. On top of that, we can see that there are very natural fluctuations that are deviating from the emissions from humans. So it shows here that it's very natural. The natural emissions, injections and removals of carbon dioxide from the atmosphere, they are actually as big, if not bigger, than the human effects. Okay, so now I also plot in the same figure. So now we start getting to the point of what this is all about. We already knew how can carbon dioxide fluctuate if carbon dioxide is caused by humans? Well, it isn't, because carbon dioxide depends on ocean temperature. That is called Henry's law. And Henry's law is the other video that I already recorded. Actually, I just did it yesterday. And please take a look at that. Henry's law can explain all the data, also in this case. Now take a look again at this curve, and now I plotted these vertical bars are years of the so-called El Niño effect. Probably you know about it. This is when the ocean surface water, especially close to, well, I think it cools down close to South America, but warms up on the rest of the planet. So an El Niño year is basically that the ocean surface water is warmer than average, and a La Niña is when the ocean surface temperature is colder. So I plotted them in this picture. A reddish bar is an El Niño, a hot year, and a bluish bar is a La Niña, which is then a cold year. And as you can see, every time that the ocean is cold, there is carbon dioxide removed from the atmosphere, or it is not growing so fast. And every time when the ocean water is warm, a lot of carbon dioxide is extra emitted into the atmosphere. Like for instance, this one here is red and it's peaking, it's red, it's peaking. It is this one is blue and it's dropping, blue it's negative. Here blue it's negative, red it's positive, red is positive, blue is negative, red is positive. There's only one exception, that is in this El Niño year, it was actually the carbon dioxide was dropping. So again, once again, something went on in 1991. to give you an idea, the effect of this, while the El Niño effect is a local, rather local phenomenon, the impact on the global temperature is the order of 0.1, 0.2 degrees. Now, if you then look at this amplitude here, then it translates to about 5 to 10 parts per million per Kelvin. That is nice. That is a little bit below what we shown in the previous video about Henry's law. So there is somewhat on this scale, on this periodicity, there is a little bit less effect, but I will come to that in a moment. The thing is that it is less, but of course there can be some delay effects. And this delay effects, as people like Indermüller has shown, is about maybe up to 1000 years. I will now present a little bit a shorter value, but the data is not so convincing that I present here. So I guess it will be sort of like 700 years is the delay between changing of the temperature and changes of carbon dioxide in the atmosphere. Yes, that is this red one is about the Pinatubo effect. Oh, now I already did a spoiler alert. This is going to be Pinatubo. After that, the temperature, after this event, we actually see that the carbon dioxide production has changed a little bit, which is a little bit strange. Okay, if we do insist on attributing the changes of ocean temperature to atmospheric CO2 changes, which is the greenhouse effect, one could say, then the question arises, why the anthropogenic emissions do not have any effect on this temperature so far and only natural fluctuations do. Because let's show at this picture here, I put not just the El Niño, La Niño values, but also put it as effect as a temperature surface. In green is the ocean surface temperatures, and in blue is the year-on-year carbon dioxide change. And then you can also see that well, the fluctuations that you have here, they're about 2 degrees, ocean surface temperature changes, and they correspond to, let's say, 1 ppm. Now, if we do insist on attributing the changes of the ocean temperature to atmospheric CO2 changes, so the other way around with the cause and effect, then the question arises why the anthropogenic emissions do not have any effect on temperature so far and only the fluctuations do. Because here the fluctuations of CO2 then changed the ocean surface temperature by about 2 degrees. And they are, let's say, 1 gigaton. No, sorry, this is in parts per million. 1 part per million change in carbon dioxide in the atmosphere causes then about 2 Kelvin ocean temperature change. But we have put much more than this 1 ppm into the atmosphere. Look again at this. We went from 320 ppm in the atmosphere to 420, or let's say 410 ppm in the atmosphere. So if the fluctuations of 1 ppm changed 2 degrees the ocean temperature, then why 110 ppm didn't change the ocean temperature at all? You understand it? That seems to be undermining the model. On the other hand, the Henry's law idea works very nice because these changes in temperature then starting, for instance, if it heats up, it starts outgassing from the oceans, and we can easily inject a couple of degrees, a couple of ppm into the atmosphere, and then we recapture them when it gets colder. And if we then take a look at this in a little bit more detail, so this is very back of the envelope calculations, because it doesn't allow for such an accurate analysis, but you get, let's say, that the idea is consistent. The data is consistent with this idea. So we have an oscillation here when you look at the data. The oscillation of the carbon dioxide in the atmosphere is about 3 years, the periodicity. And in 3 years, of course, then if you take a sinusoidal analysis of, let's say, 3 years, and if the temperature then is also changing with this 3 years, as you can see, that is of course then is the case. So a periodicity of 3 years, then the amplitude is not the maximum amplitude that you expect in infinite time, but it depends on your relaxation time of the system, which would be, let's say, 700 years, and your periodicity in your signal, which is 3 years. So you can imagine that this is then very much the total effect of the Henry's law that you would expect is very much changed, reduced, because the periodicity is very short. And I make here an estimation that it would be, the relaxation time would be 0.7 years, but I must say that because the amplitude is so small that it's very difficult to estimate. So don't take this, don't cite me on this number. Please cite the one of Intermühle, which says 700 years, or Mr. Fischer, which also says, let's say, 500 years. Okay, and one thing to finish with, on figure 6 I plotted here. This is then the year, and the amplitude, let's say go back to the initial, the amplitude of these oscillations, because they increase the amplitude of this oscillation. The seasonal oscillations are bigger here than they were here, and this we can attribute to biological activity. So we see that the amplitude has increased by about 19% in the last 60 years. 19% more bioactivity. Also, the NASA has shown that the planet has become sort of like 30% greener. Here I cannot see the surface area that got green, which NASA is doing. I check here the three-dimensional volume of bioactivity going on in the planet, and it's bioactivity, so it can be volume but also times the activity per cubic meter, because of course when the temperature increased, the bioactivity also increases. So we get actually we increased by 30% the carbon dioxide in the atmosphere, from 320 parts per million to 420 parts per million, more or less. And the bioactivity has changed by 19%. So we are tentatively saying here, it looks like there's a square root, that the bioactivity is proportional to the square root of carbon dioxide in the atmosphere. I have no idea how this could be. Maybe a biologist could explain this to us, but it's not linear. We put 30% more carbon dioxide in the atmosphere, and the bioactivity went up by 19%. And that is also, of course, the amount of life on the planet. So actually, if this carbon dioxide is partially at least due to humans contributing CO2 to the atmosphere, that would be something very good, because it increases bioactivity, and actually that would reduce the amount of hunger on this planet and poverty, because with increased bioactivity we have increased yield of crops on the planet. So by all means drive your SUV, because you're actually fertilizing the planet. Like I would like to remind you, as all agricultural farmers know, those that have real greenhouses, they inject carbon dioxide into their greenhouse to increase the productivity of their plants, the activity of their plants. And it is all to increase the amount of food in the world and to reduce hunger. So, in conclusion, I have shown here that there was an event in 1991 which perturbed the natural course of things, let's say El Niños and La Niñas, and this we attribute, I didn't say this yet, but this we attribute to the Pinatubo eruption, because that is the only thing that we can come up with that could have such a big effect. It was probably reducing the temperature of the planet, although the ocean water at that time was warmer, but probably the atmosphere was colder, and therefore it was actually removing carbon dioxide from the atmosphere. So this is why we call this the Pinatubo paper, because it sort of shows that the Pinatubo had a very big, the eruption had a very big event, was a very big event with a very big effect, and actually changed the kinetics of the natural kinetics of carbon dioxide in the atmosphere. Okay, thank you for your attention.